Thanks very much. So, yeah, thank you very much, Robert, for putting this wonderful workshop together. I'm going to tell you today about some work in my group on a decoder for error-correcting codes. This is joint work with Sturgios, Hassan, and Mark, who are all postdocs and students in my group, though Sturgios has now moved to Edinburgh, where he works with Joschka Roff. So the context of this is the general desire to build a large-scale, useful quantum computer. And it seems the most promising way to do that, certainly given some of the talks yesterday, is to make it fault-tolerant. And this is a slide I've taken from a Google presentation. It's not particularly old, it's just from a couple of years ago. And this sort of shows you their roadmap for scaling up to this large-scale quantum computer. You see the years stop there, unfortunately, so they're not going to tell you when this is going to appear. But you'll notice that we have this grid of qubits, and the grid is scaling up and up and up. And then by this point here, when you've got the person sort of standing inside the giant quantum computer, I think the implication is that this grid is enormous. And what is this grid representing? This is the surface code. And the surface code is now our most mature model of fault-tolerant quantum computation. It's the best understood. And so we can perform very detailed analyses of entire computations performed within the surface code framework. And in particular, this work was done by Michael Beveland and co-authors while he was at Microsoft. And they simulated several important applications of quantum computers and just asked the question, how big does the quantum computer need to be? How many qubits? And what will the runtime be? And you see this axis here is the number of qubits, and it's a log scale in millions. Okay, so we're talking between, if you're lucky, a mere 1 million. To do these sort of factoring algorithms, we're talking of tens of millions of qubits. So the question one might naturally ask is the surface code the right model? The surface code has this property that a single surface code patch encodes just a single logical qubit, regardless of how large you make the patch. Essentially, adding more qubits makes things more robust, but it doesn't really give you any additional logical space for your computation. And this is very different to the codes which are used in the classical world. And in particular, a family of codes known as low-density parity check codes are extremely popular these days. They're used in our mobile phones, in our wireless communications, and the adoption of codes like this is one of the reasons why the download speed from mobile phones has increased as they go from generation to generation. It's not just improvements in the hardware, it's also improvements in the codes they use. And these have the nice property that you can find good codes where as you increase n, so you increase the number of bits storing your information, not only do you increase the robustness of the code, quantified by this code distance here, but you also increase k, the number of encoded bits, the amount of encoded information. And so naturally, one would like to maybe take some of these advantages and bring them to the quantum world. And so there has been a huge amount of interest over many years in transferring these ideas to the quantum setting. But in the last 2 to 3 years, it's been a bit of a revolution. I mean, there have been paper after paper after paper, really inspired by this very important work by Panteleev and Kalichev, who showed that, yes, indeed, one can construct good quantum codes with this very promising parameter scaling. And you can imagine if one could use codes like this for large-scale quantum computation, potentially it could significantly reduce the number of physical qubits you would need for these large-scale algorithms. Okay, now, and recently, so this is a paper from 2024 from IBM, who introduced the Bivariate Bicycle codes, who are a very nice family of codes which sort of sit within this framework. They have some of the nice features of the surface code. There's a very sort of elegant mathematical framework you can use to understand them and describe them, and they're maybe a little bit less exotic than some of the codes that have the exciting properties here, but they maybe look like something that one could actually implement in the lab, and sure enough, IBM have now built their entire experimental roadmap around implementing these on their devices. So an important aspect of error correction, which is sometimes overlooked, is the decoding. What's decoding? So when the information is received by the cell tower, of course, that information has been garbled and affected by noise. And so a decoding algorithm basically runs error correction on that data. It identifies what the errors were, and it corrects them. Okay, and this is why we get a nice, clean signal when we're talking on our mobile phones. And there are a variety of algorithms which have been used for decoding. But for this family of low-density parity check codes, there's one very simple algorithm which works extremely well, and it's called belief propagation. And in the quantum setting, it turns out that a version of belief propagation also can work extremely well. So it turns out, and we'll see later in the talk, that you can use belief propagation directly on quantum LDPC codes without changing it very much. And sometimes it works very well, but sometimes it just fails. And the reason for that, really, there are several reasons, but an important part of that is that what belief propagation is doing is it's trying to work out the marginal probability for every bit or every qubit. What is the probability that there was an error on that qubit? And then from these probabilities, one can then reconstruct a correction. But when we have quantum codes, we have degeneracy, and we know that errors are all equivalent up to multiplication by elements of the stabilizer. Therefore, there are many different errors which could affect many different qubits, which, from the perspective of the quantum code, are all equivalent. And belief propagation doesn't know about that, and it sometimes leads it to get confused and make poor decisions. But what one can do is add a second decoder stage, for example, ordered statistics decoding, which you can think of as a kind of a brute force decoder, which takes the output of BP. So BP is telling it where are the errors most likely to be. And then what OSD does, it kind of focuses the attention just on the places that errors might occur. And then one can actually do a kind of a brute force inversion of the relation between the error and the syndrome using Gaussian elimination. And one achieves an output which is more likely to succeed than BP on its own. And a very nice numerical implementation of this has been created by Joschka Roffer. It's called the BP-OSD LDPC package. And this is widely used in research in this area. As people identify new codes, they can immediately use this decoder to test numerically the performance. So, for example, this is what IBM did when they proposed the Bivariate Bicycle codes. They used this decoder to test the performance. But the problem with BPOSD is it's not particularly fast. So while on the one hand, belief propagation on its own can be parallelized down to a time linear in the number of bits, OSD, the Gaussian elimination step in OSD can be a bottleneck, and this really can slow things down significantly. And there have been some alternatives to OSD proposed, which have better runtime and are more easily parallelizable. But it would be very nice if, like in the classical setting, we could decode quantum codes reliably just using belief propagation on its own. And this is what the AutDEC decoder will achieve. So the Aut in AutDEC stands for automorphism. And I'll explain to you in the next few slides how we can use these automorphisms, these symmetries in the codes, to basically translate our decoder problem into lots of equivalent but different decoder problems, such that then belief propagation will try and solve them in different ways. And by doing that, some of the decoders will work better than others. Some of them will quickly find a correct and acceptable correction. And by parallelizing these, one can therefore speed up improve the performance of belief propagation without the need for a secondary post-processing decoder. Okay, and this idea goes back to the classical world, where this has been used as a way of enhancing belief propagation and making it work faster. But we wanted to apply it to quantum codes. So what I'm going to do in my talk is give you a little explanation of how belief propagation works. It's very, very simple, and it's sort of easy to understand, and I think you'll see why it doesn't always work for quantum codes. And then I'll introduce the main ideas of AutDEC, and then show you some of the numerical results that we're able to achieve with the decoder. So what is the decoding problem? Well, in the classical world, we describe linear codes by a parity check matrix, and the rows in this matrix are literally telling you the parity checks that the code words needs to satisfy. So in particular, we can interpret this by looking along these rows, and the parity of the subset of bits with a 1 needs to be even for there not to be an error. In other words, you can detect errors by just performing the matrix product H with the transpose of the code word, and when there are no errors, this will output 0, 0, 0. And sure enough, when there are errors, this will output 1s, and this will be our syndrome that we use, that we feed into our decoder. So what the decoder is trying to do, it's trying to invert this equation. Given the syndrome, we want to find out what are the errors. And the way belief propagation works is it represents this decoding problem on a graph. So this is a graph called a tanagraph, which is a graphical representation of this parity check matrix. And there are two sets of nodes in this graph. So the data nodes represent the bits in the code, and the check nodes represent the parity check. So they represent the rows in the parity check matrix. And you can see there are edges on this graph corresponding to the presence of the 1s in the rows in the parity check matrix. So you can think of this as this node here is connected to these 4 bits, meaning that this parity check is the parity of these 4 bits. So it's very, very sort of simple representation. And what belief propagation is, it's a message passing algorithm where each one of these nodes you can think of as a little autonomous computation unit, which is going to collaborate with its friends, the other nodes, by sending messages back and forth along the lines of the tanagraph. And what everyone's trying to achieve is to work out, given a particular syndrome, what is the probability that an error has occurred on each of these bits. Okay? And it does this so initially we have to initialize it both with the syndrome and an error model, so prior probabilities for an error on each of these bits. And then what happens is these priors get sent down the tanagraph edges to the syndrome bits. The syndrome bits then look at this information, they try and reconcile it with the information they know, which is what the parity is of the bits that in this parity check. And they know, for example, if the overall parity is odd, they know that an odd number of the bits that are attached to it must have had an error. Okay, and just with some very simple calculation, what the node can do is it can look at the prior probabilities that have been sent by all of the nodes. It can exclude one of the nodes and say, okay, if I just look at the prior probabilities that the other nodes have sent, and I look at the fact that I know the overall parity is 0 or 1, I can estimate my own guess of the probability that this node has an error. Okay, so it does this calculation, and then it sends those probabilities back to every single node. So every node receives from, every data node receives from every check node a new estimate of the probability that it had an error. It then takes these messages, multiplies them together to get some sort of average, a sort of a joint probability, which represents kind of the average guess of all of the check nodes of how likely it is to have an error. And then that is the end of one cycle of belief propagation. So to finish off, what we do is we now take all of these prior probabilities and we make a hard decision, which basically means we convert these numbers to the closest integer 0 or 1, and that then represents our best guess of what the error was. So in this example, these probabilities are all still low, so our best guess here is that no errors occurred, but that's wrong. So belief propagation often needs to take multiple rounds, and at the end of each round, you check, is this hard decision compatible with the syndrome? If yes, you output the error. If it's not, you need to continue, and you just repeat the process using these new priors, and you repeat until it converges. Okay? So it's a very simple algorithm, and I think you can even see from the structure of it, it can be readily parallelized. All of these messages could be sent simultaneously, and so it can have a very sort of lightweight and fast implementation. And the nice thing is we can take these classical decoding ideas and adapt them to the quantum setting almost without modification. So, for example, we can take a quantum code where now we have X checks and Z checks, but we can represent those with parity check matrix in a very similar way. And so, for example, if we had, say, a Z error on this qubit, the Z error here will be detected by an X check which acts on this qubit, this qubit, this qubit, and this qubit. In other words, the stabilizer represented by this node on the tanagraph is flipped by the error happening on this qubit here. And that's completely analogous to the parity check in the classical code being flipped by the error happening here. So essentially, you can just wholesale import classical decoding techniques, and typically they work, but there are features of the quantum code which are not present in the classical setting, particularly this code degeneracy, which can confuse belief propagation. And so this means essentially that belief propagation sometimes fails. Okay. So here's a very simple example. This is the 15-qubit Reed-Muller code, and this is the tanagraph representing half of the checks there. So these are the X checks, which will detect Z errors. And we imagine we just have a Z error on that one qubit. We run belief propagation. It has messages sent back and forth, very quickly converges, and identifies, yes, there was an error on that qubit. So that's a nice example of belief propagation running well. But if we put a Z error on this qubit here, so the only difference is that this single qubit here is now attached to all of these 4 parity checks. So this is the one qubit in this 15 Reed-Muller code where all of the stabilizer generators have a non-trivial support on this qubit. And this kind of scenario really confuses belief propagation because it's basically all 4 of these parities are 1. So all 4 of them are thinking, oh, there's an error here, there's an error here. But all the priors are low, and essentially it oscillates backwards and forwards between them thinking all of the qubits have an error, none of the qubits have an error, all of the qubits have an error, none of the qubits have an error. So it never converges and just completely fails. And it's quite shocking that a decoder would fail for a qubit on an error on a single qubit. Okay, that sounds like a really bad decoder if it's not able to even diagnose single qubits on single errors on single qubits. But fortunately, using automorphisms, we can get around this problem, and we can transform the decoding problem into multiple equivalent but different decoding problems, run all of these decoders in parallel, and then pick the best one. And this idea of ensemble decoding, so it arose in the classical world fairly recently, actually, 2012. In this paper, they're doing something quite similar to what we do. They are using belief propagation, and they're using automorphisms to improve it. It was used very recently in the quantum setting for the first time in this nice paper from the Google group. And what they do is a rather different thing. So they have multiple decoders for the surface code, but all of those decoders are fed with slightly different error models. And so they all function slightly differently, but again, you can run them side by side, analyze which has the best outcome, and you end up with a much better performing decoder than you otherwise would have. But we are going to develop this idea of using code automorphisms. So what are automorphisms? I mean, it's a word that doesn't come up that often in quantum computing research. They are simply symmetries of a group. They are transformations of a group whereby group elements are permuted in such a way that the group structure is still preserved. So a nice simple example, if you think of the symmetry group of a triangle, if you just mirror image it, you would get maps between various different group elements, but the relationship between the group elements is going to be retained under that symmetry. And so automorphisms form their own group, the automorphism group, and this is a useful and widely studied tool in group theory, and was brought quite early into the theory of error-correcting codes. So a code automorphism is defined as a permutation of bits which keeps the code preserved. So that means code words are mapped to code words under these permutations. So here's an example. If we have these 4 code words here, this is for the 7-bit Hamming code. If we swap these 2 columns and these 2 columns, we get back these code words here, and you can check these are all in the code. You see some of the code words have changed, but we're still remaining in the code. So this is an example of an automorphism of the Hamming code. And automorphisms are very well studied when people study properties of error-correcting codes. And algorithms have been developed to do so. The most performant of these is known as Leon's algorithm, and it's implemented in some software called Magma. And you can feed it with rather large codes, and it will take a little bit of time, but then output the automorphism group for that code. It's not an efficient algorithm, and the scaling is rather horrible in the size of the code, and it's not something you want to apply to very large codes, but you can apply it to small codes, and it works very well. So the nice thing is that one can think of these permutations from the perspective of the code or from the perspective of the parity check. And because we're still in the same code, the parity check matrix is still valid. And so when we apply a permutation, we can then afterwards apply the same parity check. And in such a way, if one were to take a code word, apply a automorphism permutation, one gets back a new decoding problem, which you can send to your decoder. It's an equivalent decoding problem, but it's a different decoding problem. And now your decoder could try and solve this problem. And then at the end, you could apply the inverse permutation, and you'd get back the correction to the original error that you received. Now, automorphisms have been well studied for a long time for classical codes, but you can also define them for quantum codes, and all the way back to 2007, these have been studied for quantum codes. They have a nice feature that they often lead to logical gates. So one can use code automorphisms as a way of finding fault-tolerant gates for a code, but we're going to use them for decoding. And if we go back to this example, where we had this single error on the 15-qubit code, which was undecoded, which was not correctly decoded by belief propagation. If we apply an automorphism, that transforms this single qubit error to this single qubit error, and the and belief propagation will now correctly decode it. So what we can do is now develop an ensemble decoder where we study the automorphism group of a code. We sample from the automorphisms for a particular code, apply them to the code, and then run our belief propagation decoders in parallel. And then at the end, we look at the outputs here, and we select the best one. We know what the error statistics are for our code, so we can, for our error model, so we can say which of these errors was most likely to have occurred. And this is the idea in this paper from Geiselhardt et al. Now, these permutations seem a bit problematic because they would correspond to physical swap gates on your code, and you don't want your decoding method to introduce extra physical gates on your qubits. This would lead to extra errors. But fortunately, you don't need to do that, and it turns out that you can apply your automorphism either by permuting qubits or permuting bits, or equivalently, you can perform a linear transformation on the parity check matrix. And it turns out those two things are equivalent. And the nice thing is the linear transformation on the parity check matrix also corresponds to a linear transformation on the syndrome, and it means that we can do that offline. So we make our measurements on our quantum system, on our quantum code, receive the syndrome, and then perform this linear transformation, and then send that to the decoder. And that way, we can set up this ensemble decoder with many copies of belief propagation, and where each case we started with the same syndrome, but this linear transformation, which has come from sampling automorphisms, presents each of these belief propagation decoders with a different decoding problem. And then some of them will succeed, some of them will fail. The ones that succeed, we analyze the errors that they have predicted, and then we select the most likely one according to our error model. So just to finish, let me show you how this works in practice. So this is a very simple test with a 15-qubit Reed-Muller code. You can see the blue arrow here is what belief propagation gets. So we've got the logical error rate on this axis, the physical error rate on this axis. So we want, ideally, our logical error to be significantly lower than our physical error. And you see belief propagation performs pretty badly. Okay, it sort of hardly reduces the error at all. BPOSD, on the other hand, brings you right down here. And our AutDEC decoder with 5 ensemble with an ensemble size of 5 parallel decoders is able to match BPOSD. So we're able to match that sort of leading BPOSD decoder, but with an algorithm which you can parallelize to linear time. Now, I mentioned that automorphism groups were hard to calculate, and this exposes a potential problem with this approach. When we want to apply this in practice, we don't want to use these simple code capacity error models. So this is an error model which assumes that none of the measurements have an error, okay? A much more realistic approach is to assume that every single gate on your quantum computer can have an error. And this leads you to something called a detector error model. And it essentially gives you a new tanagraph, which is much, much, much bigger, now containing all possible errors that could occur in your computation. And unfortunately, this thing is now this code is still effectively a classical code, but this code is way too big for us to calculate automorphism groups. So it seems like for this very important practical scenario, we wouldn't be able to apply this decoder. But there is some good news, and that is we don't have to use the full code automorphism group. It turns out we can use graph automorphisms of the tanagraph, and these are small enough and easy enough to calculate that we can compute them quite quickly. And with this reduced set of automorphisms, this decoder approach still works pretty well. So we can apply it to large codes under circuit level noise, and it still performs well. So this is just the time it takes for a variety of codes and error models, how long it takes to actually compute the automorphism group. Okay, and so this is the sort of results we achieve. So these are the Bivariate Bicycle codes introduced by IBM, and they're a nice family of codes to study. This is sort of the results that IBM obtained, and they get this nice sort of crossing here, this threshold behavior with BPOSD. And AutBP performs very similarly. I mean, it's slightly worse in terms of the logical error rate, but it's rather similar. We get the crossing in a similar place. These numbers here represent the number of parallel decoders we're using, and you can see it is increasing, but it's not increasing too badly. And it's far outperforming the original BP decoder. Okay. And what we can also do is improve its accuracy by combining it with OSD. Okay, this will then slow down the performance, but this then supercharges the accuracy. So this is some very recent work which Sturgios has done together with Joschka Roffer, and they have a nice collaboration with NVIDIA and can use their sort of GPU supercomputers. And so they were able to do this simulation on some very big Bivariate Bicycle codes of this AutDEC together with OSD, and what they find is that the accuracy of the decoder is an order of magnitude better than BPOSD is able to achieve on its own. So you can use this decoder together with OSD, and then you gain an extremely accurate decoder which significantly outperforms BPOSD. Okay, so I think I'm out of time, so let me summarize there. We're using automorphisms to generate equivalent but different versions of our decoding problem, which allows us to run many copies of belief propagation in parallel. And we've seen that this leads to enhanced performance. Works very well for codes with rich automorphism groups. And fortunately, some of the quantum LDPC codes that people are particularly interested in, such as the Bivariate Bicycle codes, do have just a sort of structure to work very well with AutDEC. In terms of the open questions, the biggest open question theoretically is at the moment we don't have any good analytical bounds for the resource scaling in terms of the number of parallel instances you need of the decoder within the ensemble. And we'd like to understand that a lot better. It would also be good to use these insights to de-randomize. So rather than picking automorphisms at random, it would be very nice to be able to sort of look at the structure of BP, look at the automorphism and say, okay, this is the automorphism you need to choose. And this would lead to a much more highly performant deterministic belief propagation decoder. Yes, ensembling itself can be very powerful. And I'd just like to mention two papers which have appeared more recently, which use ensembling in different ways. So this vibe decoding paper has come from Joschka Roffer's group, and this uses just ensembles over different orderings of operations in BP in order to vastly improve performance for color code decoding. And there's this nice paper from the IBM group, Relay BP, which uses a different form of ensembling, again, over sort of different modifications of BP. And that also allows you to run belief propagation as a decoder on its own with some of these very important quantum LDPC codes. So thank you very much for listening, and yeah, here are my co-authors, and also special thanks to Joschka Roffer for this recent collaboration and giving us access to these NVIDIA GPUs. But thank you very much for listening.
So maybe one quick question. Yes.
Wonderful talk. Thanks so much indeed. That was great. How does this new decoder compare to this kind of localized statistics decoding in performance? Because you also mentioned that it's kind of not so easy to see the parallel instances to be used in the decoder to bound that. And in this kind of localized statistics decoding, the point is that you can like look at clusters and then use like calculation ideas to see how many of them you need to kind of stitch it together. I mean, would a similar idea also work in your setting? And could this even be combined in a bigger framework?
So we have also combined AutDEC with the LSD decoder as well. I mean, at the moment, both our implementation and the LSD implementation are not parallelized, so you don't get the full runtime improvement. But nevertheless, it works. I mean, they work in very different ways, and both are aiming to kind of get around this, this Gaussian elimination bottleneck. So we do it by not doing the Gaussian elimination at all, so there's no OSD in straightforward AutDEC, whereas LSD has a sort of a simplified and faster and parallelized implementation of that step. But you certainly can use them together, and we have tested them together, and they perform very well together.
All right, so let's thank Ben again.
Thank you.